Hey, good morning. So today we're going to talk about epipolar geometry and stereo vision, which is relating two cameras from different positions. So last class we talked about image stitching, and which is trying to relate two cameras that are taken, or two images that are taken from the same position but different orientations, and then using that relation to project all the pixels onto the same surface. And then we went through a lot of the techniques that we've discussed in previous lectures, like solving for the homography, using direct linear transform, and using Laplacian pyramids to do blending and other algorithms. So today we're going to talk about two-view geometry, and if there's time, I'll start to get into structure from motion a little bit. But mostly we're going to do just assume that we have two cameras that are taken from different positions, and then we want to relate those cameras to each other so that we can estimate depth, and we may care about the camera positions by themselves as well. So there's two main components that we'll talk about. One is epipolar geometry, which is how we relate cameras from two different positions, and then how we estimate depth given two cameras that we've registered to each other, which is stereo depth estimation. So in order to estimate depth, in order to estimate depth based on correspondence, you need to be able to recover the position of one camera relative to the other, and then find corresponding points. And then if you can do that, then based on the position at which you observe each of the points, and you can triangulate to solve for the 3D position of the point. So the simplest case is if you have two cameras that are just translated with respect to each other, and then you can find, then the corresponding points will just be different pixels at different columns, so there'll be some disparity that's horizontal. And then the disparity is inversely proportional to the depth of the 3D point. So in order to recover stereo, we have to solve for it. In order to do stereo, we have to recover the camera positions and then find corresponding points, and then we can compute the depth of those points. So we have to deal with the calibration, which is recovering the relation of the cameras. And sometimes you might have a stereo pair where you already are given that because the cameras are fixed relative to each other. But other times you need to solve for it. And we need to solve for the correspondence, which is finding the matching point. So let's say that we want to do this corresponding problem. So first I'm just kind of motivating it a little bit with stereo, and then we're going to jump into the epipolar geometry. But let's say that I've got these two cameras. Let's just say that they're registered for now. And I want to find the corresponding point to this x on the left side. So what is one method that I could do? Yes?
You do a key point detector, and then when you get the key points, then do ransack or some routing out.
Yeah, so one thing I could do is just try to do a key point detection and matching. That's actually used for structure from motion, where you have a lot of cameras taken from very different positions. But often we want really dense matches, even denser than key points will detect. So we want to just say, given some pixel, find the corresponding pixel in the other image. There's another kind of simple technique that we've talked about, though, that we could apply. Right, template matching. So we could just extract a patch around the x and then search over the image to try to find the position in the second image that has the minimum squared distance to a patch around the first image. Now, you can imagine that if you had to do this for every pixel, it would be, and you're searching over the whole image, it would be really slow. So we need some way to constrain our search. Ideally, we don't want to have to search over every single pixel in the other image. If we know some relation between the cameras, then maybe we can constrain the set of possible pixels where the corresponding point can lie. And so that's the basis of, or that's what the epipolar geometry and the epipolar constraints give us. So here's the setup for stereo, or for two-view geometry, epipolar geometry. We've got some, whoops. Drew my camera facing the wrong way. We've got a camera over here. No, I drew it the wrong way again. Sorry. This was right. Okay. We've got a camera over here and a camera over here, and so they're sort of facing inward a little bit so that they're looking at the same point in the scene. And then I've got some 3D point in the scene that they can both observe. I'm calling that big X. Let's see if I'm going to zoom in a little bit because it seems like it does a little better when it's a little zoomed in. Okay, so I've got a 3D point in the scene. The point at which that's observed in this first image will be along the ray that passes from the camera center of the first image through the 3D point. Okay, so it hits it at some position here. So this is the camera center of the first image. And this is the point where it hits in the first image. And so the problem is that I want to try to see where it will project in the second image. Or if I want to solve for, I want to establish a constraint between where the point occurs in the first image and where it occurs in the second image. Now, I, of course, don't know the value of the 3D point. All I know is the pixel that it projected through. And so what that tells me is that the 3D point is somewhere along this ray, the ray going from the camera center through this pixel. You can think of this, even though the pixel is a 2D coordinate, you can think of this as a 3D ray, a ray from the 3D camera center through that part of the image plane. So we've got this ray. And if you think about all the possible values, all the positions that this 3D point could occupy and project them onto the second image, so it could be here, for example, which would be like here, or it could be here, or it could be here. So all of these, if you look at all of these positions, they're going to form a line, right? Because the projection of a 3D ray onto the 2D image is a line, because lines are preserved in perspective projection. Now, if I had a different point, then again, that's going to, of course, project to a different position in the first image. And again, all the places where that could project in the second image will also be along some line. So, but there's something that all of these lines will have in common, which is that note that all of these 3D rays have something in common that go through the first image, which is that they all have to intersect at the first camera center. And likewise, for all these points, when they're projecting back into this image for the true values, they're all going to project into the second camera center. And so what that means is that they're all going to have, if you form a bunch of triangles from the 3D point to each of the camera centers, then all of these triangles, these 3D triangles, are going to have in common this baseline. Right? Because if I form some 3D point up here, you can think of it as I've got some plane that goes through this pixel, the 3D point, the pixel in the other image, and the two camera centers. Some other 3D point, again, will form some 3D plane that goes through the second 3D point, the two camera centers, and the pixels. And for any 3D point that I choose, it's going to, if I draw that triangle between where it projects in each image, it's always going to project through the camera centers, and so this baseline will always be a line on that plane. And in fact, all of these lines here, these lines are called epipolar lines. They're the lines of the projection of the ray through a pixel onto the other image plane. All of these epipolar lines are going to intersect at some point, which is the, should be down here, which is the position where the image plane intersects with the baseline between the cameras. Right? Because this is the line that's in common from all planes through the 3D points and through the camera centers will intersect at this baseline. So all projections of the rays through the 3D points will also intersect with that baseline, and they'll intersect at this position, which is called the epipole. So this is the epipole of the second camera, and this is the epipole of the first camera. And so what epipolar geometry gives us is that once we can solve for the relation between the cameras, then given a point in one image, we know that it's going to project onto some line through the epipole of the second image. Or given a point in the second image, we know that its corresponding point is going to project on some line through the epipole of the first image. So I've got it illustrated here as well. Right, so this is just another illustration of the same idea. We've got the two camera centers. We've got this ray that's a ray through the observed pixel in the first image, and the true 3D point will be somewhere along that ray. We don't initially know the 3D point, but what we do know is that the projection of that ray onto the second image will intersect with the baseline between the cameras. And the place where the baseline intersects with the image planes is called the epipoles. So basically, solving for those epipoles gives us a relation between the cameras. Yeah, so this is just illustrating that. Great. So just a little bit of notation. The baseline, which I'll say a lot, is the line that connects the two camera centers. It's a 3D line. The epipoles are the intersection of the baseline with the image planes. Here it's drawn so that they intersect within the actual image, but as in my drawing, they didn't intersect within the image, and that's fine. And you can imagine if the cameras are parallel, then their baseline is going to be parallel to the image plane, so it'll be at infinity. So you can think of it as, another way to think of it is that it's a projection of the other camera onto the image plane. So it's basically where you see that other camera. But it might be outside of the image extent. The epipolar plane is a plane containing the baseline. So there's a whole set of these planes that are rotating around the baseline. And the epipolar lines are the intersection of an epipolar plane with the image. So for every 3D point, there'll be a pair of epipolar lines in the two images. And or actually I should say, for every projection of the 3D point in one image, there'll be an epipolar line in the other image. Right? So given x prime, there'll be a particular, given x prime, once we solve for the relative camera, then we can get L, the epipolar line in the first image. And given little x, we can get L prime, the epipolar line in the second image. So here's a couple of examples of these epipoles. So you can see that there's a few corresponding points here. And in this case, the cameras are facing each other. And so And what's shown here is the corresponding points and the epipoles. So this is given this point, this is the epipolar line in the second image. Given this point, this is the epipolar line in the second image. And the corresponding point has to lie somewhere along that line. So that means that when you're doing a stereo search, then you only have to search along a line. You don't have to search in the whole image. So here's another example where if the motion is parallel to the image plane, and by motion I just mean the relative position of the cameras, then the epipolar lines will all be parallel because the epipoles will be at infinity. Because if I've got my two cameras here and the baseline's here, then I've got, the place where those intersect at the image plane is at infinity because it is parallel. So what would the epipolar lines look like if the camera were to move directly forward? Or another way to say it is, where would the epipole be? So, yes? Yeah, it would be at the camera center. So remember that the epipole is basically the projection of one camera center onto the other image plane. And so if they're moving forward, if they're moving exactly forward, then one camera center is just going to project onto the principal point or the center of the other image, and vice versa. So this is an example. So these are the epipolar lines for these two images, and they all intersect at some, it's a forward motion. They all are at some central point in the image. So this epipolar constraint it's the fundamental relationship and constraint between the two images. So how do we recover it? So let's first take the calibrated case. So that means that we're going to assume that we know the intrinsic parameters of each camera. We know the focal length and the principal point. And if there's any radial distortion, then we've already undistorted the images to take care of that. So we have the intrinsic matrices are K and K prime for the first and second images. I'm going to tend to use the non-prime and prime to denote the two images. And we can solve for, the first thing we do when we know the intrinsic matrix is pre-multiply each of our 2D points, which would be UV1, by the inverse matrix. So basically, remember that little x equals k times big X from our single view camera equations, right? And so if we pre-multiply each side, then we get k inverse x, little x on one side, and big X on the other side. And what we get is this x hat, which is the homogeneous 2D point, which is actually a ray from the camera center through this point. Because remember, everything's defined up to a scale, so a 2D point in homogeneous coordinates is just a ray in 3D coordinates. So k inverse little x is this ray that goes from the camera center through this pixel and through the 3D point that is imaging onto the pixel. And then likewise, we can pre-multiply a corresponding point in the other image by its inverse intrinsic matrix to give us the ray from that camera center through the other point. And so now we have x and x prime. And if we know that these two 2D points correspond, then big X equals big X prime. And so we have a constraint between the cameras. We know that there's some relation between x hat and x hat prime. So let's look at what that relation is. So what we're trying to solve for now, given that we know the intrinsic matrix, we want to solve for some rotation and translation between the two cameras. So we know that we want to solve for a rotation and translation such that when we apply the rotation to this vector going from the camera center through this pixel, and the translation, then it brings us into this vector that goes from this camera center through this pixel. So we want to solve for some R and T that relate x hat prime to x hat, which are the normalized 2D coordinates, or like the rays going through the corresponding pixels. Right, and this is just putting the same equations. So one thing, so we have some R and T such that x hat equals r x hat prime plus t. And from just based on simple geometry, we can get that x hat dot t cross r x hat prime is equal to 0. And so to see that, note that r x hat prime is going to be on the same plane as this triangle here, right? T is on the same plane as this triangle, so that means that t cross r x hat prime is perpendicular, right? Because if you take the cross product of two vectors, you get a vector that's perpendicular to them. And because this is perpendicular to this plane, and x hat is also on this plane, where x hat is this vector from this camera center through the corresponding point, then x hat dot that direction perpendicular to the plane must be equal to 0. And so this gives us our constraint. And this is just another way of, this is basically saying that x hat will be on the epipolar line that corresponds to this, this other image. So we can rewrite this into a form that's a little bit more convenient. Instead of writing it in terms of R and T, we can write, we'll write it in terms of E. And E is called the essential matrix. So E is just the skew symmetric matrix of T times R. So this is just, if I have like T cross R x hat, I can rewrite this in terms of a matrix operation on x hat prime, which is the skew symmetric matrix of T times R. And I don't have the skew symmetric matrix here, but it's a 3x3 matrix that places the elements of T in that matrix so that it gives you the same result as if you took the cross product with R. Right. So the essential matrix was first described by Longet-Higgins in 1981, and it's one of the most basic concepts in general stereo. Right, so here's some properties of this essential matrix E. And here I'm dropping the hat, so all of these x's are still pre-multiplied by the inverse intrinsic matrices. So Ex prime is the epipolar line associated with x prime. So if I solve for this matrix E and multiply it by this point x prime, which has been pre-multiplied by k prime inverse, then it gives me this line L. Likewise, E transpose x is the epipolar line associated with x. So if I do E transpose times this point, I get this line. E times E prime and E times E. So if I multiply it by the epipoles, I get 0. Because these epipoles are always going to be, these epipoles are going to be on any epipolar line that I draw. And E is singular rank 2, which is clear because there's because I've got some null vector there. And so E has 5 degrees of freedom. So it kind of makes sense that it has 5 degrees of freedom because remember that it's encoding a rotation matrix and a translation vector, but everything is up to a scale. So if I were to shrink my scene in my cameras or make it a lot bigger, I'm going to get the exact same images. So I can only solve for things up to a scale. And also I can really only solve for things up to a similarity transform because I'm solving for the rotation and translation of one camera with respect to the other. But if the entire scene and cameras rotate or translate, I'm going to get the exact same image. So when I solve for E, I'm going to get it has 5 degrees of freedom, which correspond to the 3 rotation angles and the 3 translation parameters up to a scale. So I'm going to get to how to solve for this in a little bit. But first, what if I don't know k and k prime? So if I don't know k and k prime, the intrinsic matrices, then I have a very similar relationship, but I've just got what's called the fundamental matrix, which has more parameters. So if I don't know k and k prime, then I just have x equals kx hat and x prime equals k prime x hat prime. So if I then substitute into my expression for the essential matrix here, then I just get x transpose fx prime equals 0, where f is k inverse transpose e k prime inverse. Right? So it's just a simple substitution of k inverse x into here and k prime inverse x prime into here. This is called the fundamental matrix. And that was first described by Fourgeat and Long in 1992. So the fundamental matrix, the essential matrix, relates two cameras where I know the intrinsics, where I know the focal length and principal point. The fundamental matrix relates two cameras where I don't know the intrinsics. So obviously it will have more parameters. So here are some of the properties of the fundamental matrix. So we've got, it's very similar to the essential, except that now the points are not pre-normalized with the inverse intrinsic. So fx prime is the epipolar line associated with x prime. And here I mean this 2D coordinate, not the ray coming from this camera center. And f transpose x is the epipolar line associated with x. And fe prime is still equal to 0, and f transpose e is still equal to 0. So I still have f as singular, rank 2, which means that the determinant of f is equal to 0. And f has 7 degrees of freedom. So it has 9 entries, but it's defined up to a scale, which removes 1 degree of freedom. And also the determinant of f is equal to 0, which removes another degree of freedom. E has additional constraints on it. For example, both of the two non-zero singular values must be equal. And then there's additional constraints that brings it down to 5 degrees of freedom. All right, so now how do we estimate the fundamental matrix? The most common algorithm that's used is the 8-point algorithm, which is just a least squares solution using SVD from 8 correspondences. So I'll get into that in a moment, but note that we have this equation x transpose fx prime equals 0. And so that gives me, for every pair of corresponding points, I have a single equation. I'm always going to get some coefficients times the variables that I want to solve for is equal to 0. So it's a homogeneous system of equations. And so I can solve for the 9 entries of the 3x3 matrix F with 8 of these equations, or with 8 corresponding points. So that's where the name, the 8-point algorithm, comes from, because we need 8 points to solve for it. And I'll go through it in a little more detail, but it's basically just using, once you set up your matrix AX equals 0 or AF equals 0, then you use SVD to get the null vector, and then enforce that the determinant of F is equal to 0, again using SVD on F and setting the last singular value to 0. Then there's another algorithm called the 7-point algorithm, which is using least squares to solve for the two null space vectors of F, since F only has 7 degrees of freedom, and then solving for a linear combination of the null space vectors that satisfies that the determinant of F must be 0. And then the third algorithm is to try to minimize the reprojection error. So I'll get into the 8-point algorithm in a moment, but one thing to note is that trying to estimate F or E is degenerate for a planar scene. So if all of your 3D points that are imaging onto your corresponding points are on the same plane, then then you can't solve for F. Then there are many valid solutions for F, and so you're going to get some random solution, and it's easy to detect that your solution is invalid, because if you draw your epipolar lines, then they won't intersect at a single point. But that's just an important thing to know, that if I have two images of this wall, I can't solve for the relation between those images. And that's because there's basically I'm solving for the relation between points on this plane and points on this plane. But if all of the 3D points that are imaging onto them is just another plane, then there's some kind of ambiguity between the projection onto these planes and the projection onto that plane. And so I end up with an under-constrained solution. So here's the 8-point algorithm. It looks very similar to the algorithm that we use for solving for the homography. We've got x transpose fx prime is equal to 0. If I multiply that out and turn it into a long line, then I get this equation here where I have a set of coefficients. Here u prime, and v prime are the points that I know that are corresponding. And so then when I put this into matrix form with 8 points, I'll get my matrix A here, which will be an 8 by 9 matrix. And then F, which has 9 elements for the 9 elements of the 3 by 3 matrix F. And that's equal to 0. I solve for it using SVD, the same way that we've done many times. Take the last column of V, which will correspond to the smallest singular value, which will be 0. Then reshape F to be a 3 by 3 matrix. I'm doing the transpose because the way I ordered it here was F11, F2, 1, 2, 1, 3. But when I do reshape it, we'll reorder it in the transpose. So I take the transpose so that I get the right elements in the right places. And so that's the first part of the 8-point algorithm. Almost identical, well, extremely similar, following the same pattern as the algorithm that we talked about for solving for the homography. So at this point, though, I haven't enforced all my constraints. So the determinant of f must be equal to 0, but the solution that I get for f will not have a determinant of 0. And so the consequence of that is that I'll have, if I draw my epipolar lines, they won't exactly coincide because I won't have solved for the true, a valid fundamental matrix. And so we want to force the determinant of f to be equal to 0 so that the lines coincide. And we can do that very simply using SVD. So we just decompose it into u singular value v, force the last singular value to be 0, which is actually corresponds to solving for the f that has a least squares similarity to the original f, but the last singular value is 0. And then I just recompose f out of us and v. And now this gives me an f that's very close to the original f, except that the last singular value is 0, meaning that so that the determinant of f will be equal to 0. And that will fix the problem. And then the last note is that just like when we were solving for the homography, it's important to normalize the coordinates because solving for least squares constraints in a homogeneous space doesn't correspond to reprojective error. And so we want to make the scale parameters and the u and v parameters to be all similar. And so you would want to, before solving for the fundamental matrix, you want to normalize all of your points by subtracting the mean and dividing by the standard deviation. And then we can use ransack to solve. If we've got just a set of corresponding points and some of them might be outliers, then we use ransack to remove the outliers and solve for f based on the inliers. Right, so I just want to summarize this so far by comparing the homography estimation and the 8-point algorithm. So we assume that we have matched points. X matches x prime with a set of outliers. So when we're solving for the homography, which has no translation, or the fundamental matrix that has translation. So for the homography, we would establish this correspondence relation, which is x prime equals hx, which I could also write as x prime cross hx equals 0. Then I normalize the image coordinates by finding the transformation for each set of images so that the average of the points is 0 and the standard deviation is 1. Then I do ransack with 4 points, and I get and then I can find the solution using SVD. And then at the end, I denormalize by taking this is the homography of the normalized points, and then I unnormalize it by solving using these expressions here. Similarly, for the fundamental matrix, the correspondence relation is that x prime transpose fx equals 0. So now every pair of points gave me 2 equations. Here it gives me 1, or it gave me 2 constraints in the case of the homography. Now it gives me 1, so I need 8 points. I go through the same process and normalize the image coordinates. Then I do ransack with 8 points. I get an initial solution with SVD. And then I enforce the constraint that the determinant of f must be 0, again using SVD, as I showed in the last slide. And then I denormalize, again just substituting tx and t prime x prime for x tilde and x tilde prime. It's a very similar process. So the 7-point algorithm starts out the same way as the 8-point algorithm, where you set up your matrix AF equals 0. But then you take two null vectors of your coefficient matrix here, and then f has to be some linear combination of those 2 null vectors. So you solve for the lambda and mu of those null vectors such that the determinant of f is equal to 0. And you either get 1 or 3 real solutions. Depending on, actually I'm not sure exactly what it depends on, but you either get 1 or 3 real solutions. So the 7-point algorithm can be faster because you need fewer corresponding points. It can also potentially be more robust because if you need fewer corresponding points, then the chance that you'll randomly sample seven truly corresponding points is higher than that you'll sample 8 truly corresponding points. And so you need to do less iterations, and if there are a few corresponding points that you have between 2 images, you have a better chance of success with the 7-point algorithm. But then you need to check for degenerate cases where you might have multiple real solutions. And so in practice, most people just use the 8-point algorithm. The gold standard is to first use the 8-point algorithm to get an initial value of the fundamental matrix. Then solve for the projection matrix between the 2 cameras, which I'll show a little bit later. And then jointly solve for the 3D points and the fundamental matrix that minimizes the squared reprojection error. So they use the linear solution for f, because that's really fast, and you can quickly find the inliers. Then once you find the inliers, then you try to minimize the reprojection error of the points onto the image based on a solution for both f and x. And that's going to be a nonlinear solution. So this is just comparing the 8-point. This is comparing how good your solution is for the 8-point algorithm, normalized 8-point algorithm, and nonlinear least squares. So the error measure is the distance of the points to the corresponding epipolar lines. So for the 8-point algorithm, if you don't normalize, you get a pretty big error. On average, the points are 2 pixels away from the epipolar lines. If you do normalize, then the solution is much closer. On average, the corresponding points are less than 1 pixel away. And then if you do nonlinear least squares to adjust your solution for the fundamental matrix and the values of the 3D points, then you reduce the error further. So given a fundamental matrix, we can solve for a relation between the cameras, but up to some projective ambiguity. So remember that if we had the essential matrix, then we could solve for the rotation and translation up to some scale. If we only have the fundamental matrix and we don't know the intrinsic parameters, then what we're really getting is k times some rotation or k prime times some rotation and k and some translation. So we don't know the true rotation and translation. We only know it up to some factor that depends on the intrinsic parameters. But we can solve for this projection P, which is just using this simple, this code is from VGG, which is the visual geometry group. And it's taking I think this is the skew symmetric matrix of E times F, and then E, where E is the right null vector of F. And then if we know the intrinsic matrices, then we can resolve the ambiguity. So if we're given a matrix F, we'll usually say that the first projection matrix, the projection matrix of the first image is just identity for rotation and 0 for translation. And then we can solve for a projection matrix of the second image, but it's going to have some projective ambiguity, which means that we can multiply all the 3D points by some matrix, and then post-multiply our projective matrix by that inverse. Okay, so let's say that I pre-multiply all my 3D points by M and post-multiply my projective matrix by M inverse, then I'm going to get the same projection. And so I can create any invertible M and get the same projection. And so the values that I solve for my 3D points and projection will not necessarily be the true 3D points up to a similarity. And likewise, my projection matrix will not necessarily correspond to my rotation and translation because there's still some ambiguity there. All right, so I know this is all a lot to take in, so I want to show this as a recap. I'll do the fundamental matrix song, which obviously, as you'll see, I did not write. But it's a pretty good summary and very, very concise. To make sure the audio is working. I need to do, how do I do this? Let me see. Sorry, I need to see if I can get some audio. Bear with me for one moment. All right. So this is the best summary of a computer vision algorithm by song that I know of. Let's hope that the audio... Oh, no. OK, let me see. Audio.
The fundamental matrix used in stereo geometry. The fundamental matrix used in stereo geometry. A matrix with 9 entries. It's square with size 3 by 3. Has 7 degrees of freedom. It has a rank efficiency. It's only of rank 2. Call the matrix F and you'll see 2 points that correspond. Column vectors called X and X prime. X prime transpose times F times X equals 0 every time. The epipolar constraint involves epipolar lines. Post multiplying F by X results in vector L prime. It's the epipolar line. The other two passing through X prime. The 3-component vector of homogeneous design. The left and right null spaces of F are the epipoles E prime and E. All of the epipoles observation example. Take a set of 8-point samples. Construct a matrix, take the SVD and the element of F in the last column of V.
Doing the epipolar lines, tracking the. Show that part.
Try to estimate F with a coplanar set of points. Your sample set will be degenerate. That will not bring you joy. When doing the estimation, if you don't perform rank deprivation, your epipolar lines and the epipoles will not coincide. But if your scene has 3 views, the trifocal tensor is what you use. Constraints from the 3rd view patch like blue that can't be determined from just 2 views.
Yeah, so I can't do a better summary than that in 2 minutes. So at the end here is talking about the trifocal tensor. So there's a generalization of the epipolar geometry, which is when you have 3 cameras and corresponding points between those 3 cameras. And that's called the trifocal tensor, which relates all pairs of views to each other. I'm not covering that in this class because it's a little bit more esoteric. It's not used quite as much. But sometimes Hartley's isomer covers it pretty well. But that's sometimes used for doing global SFM. So there are some kinds of SFM solutions where you're trying to solve for all the parameters and 3D points at the same time. And the trifocal tensor gives you a stronger constraint than the pairwise epipolar constraints because it's enforcing the pairwise constraints among all 3 views at the same time. And so if you get really into SFM and you're doing like global SFM research, then you would need to know that. But it will only take you about half an hour to learn it, or an hour. So now we've solved for the constraints between the 2 images, which is either in the form of a fundamental matrix, in which case I still need to get some intrinsic matrix in order to resolve my parameters, or in terms of the essential matrix. And so for now, let's assume that we've got the essential matrix. And so we've got the rotation and translation between 2 corresponding images. And now we want to produce a depth map, a dense depth map from those images. So we want to try to fuse my binocular stereo pair and into a depth image. So this is showing the depth image on the bottom, where white are pixels that are close to us and black are pixels that are further away. Okay. So the basic stereo matching algorithm now is just for every pixel in the first image, we find the corresponding epipolar line in the second image, and we search along that epipolar line for the corresponding point. So now if we're doing, instead of doing template matching over the whole image, we're just constrained to that line. And then we pick the best match. So I search across that line. I pick the best match. Obviously, you'd want to search every pixel, not just every 20 pixels. And then we can triangulate the match to get the depth information, because now we've got 2 rays from each camera center through corresponding pixels. If we find where those rays intersect, that gives us the depth. The simplest case is that the epipolar lines are scan lines. And I guess I've already said this, as this will happen whenever the planes are parallel to each other. So well, actually, there's more constraints. So I guess I will ask you. So what are all the things that have to be true in order for the epipolar lines to be scan lines, which means that the corresponding point will be on the same row in the other image? So what's their, if I'm relating the second image to the first one by some rotation and translation, then what is R and what is T? So, all right, so first, what is R? All right, so if I've got, so first of all, if the epipolar lines are just scan lines, they're going to be parallel, which means that definitely the image planes have to be parallel to each other, and I have the same, the image planes just have to be parallel to each other, the image planes must be parallel to each other, and the camera centers must be parallel to the image plane. So they should be parallel to each other, and I should have the same focal length. And so then if I draw a line through the camera centers, then it's going to, it'll be parallel then to the image planes. So the rotation matrices have to be identity. They have to have the same angle, right? The other constraint is that the second camera has to be only translated in the x direction, right? Because if it's translated in the vertical direction, then the epipolar lines will still be horizontal, but the position of one camera, the position of the corresponding point in the second image will be shifted vertically. So that means that my translation vector must be some tx 0, 0, and my rotation must be identity. And the focal lengths have to be the same, because otherwise one camera center would be shifted with respect to the other camera center. And so you can look at this, if you just do the math, if you have rotation is identity and translation is 0, and then I compute my epipolar line by the skew symmetric matrix of T times R, then I just get that E is equal to this matrix here, which just has 2 non-zero entries. Then if I multiply that matrix by U prime V prime 1, I get out that, that TV is equal to TV prime, which just means that, that every corresponding point will be on the same row as its match. So corresponding points will all be on the same rows as each other. The y-coordinates of corresponding points are the same. Okay, so now let's assume that we've got this case, and then we want to try to solve for the 3D depth value given the disparity image. So we can do that just using similar triangles. So let me just switch to my document camera. Okay, so I've got some. On the screen. Oh man, it's got to go through the paces. Let's zoom in. I don't know why, but it seems like when I'm zoomed in, it's half. Whoop. Maybe not. I thought it was usually happier. Oh, there. Okay. All right. So I've got some 3D point here. It's going to project to each of my camera centers through this image plane. So now I'm kind of looking at it from a top-down view, or I really am looking at it from a top-down view. This is the baseline between the cameras. You should be at the same distance away from the image. This is my focal length, F. So this is B, my baseline, the 3D distance between the cameras. This is F, my focal length, which is also in meters here. And then this is my 3D point X. And I want to solve for Z, the depth of that point. Right. And so if I just take these, note that if I just move these two little triangles inward, then I've got some similar triangle here. So I've got F in the vertical direction, and then I've got some disparity here. this will correspond, this will be the same as the distance between the pixels. So this is my disparity. This is my focal length. Then on the larger triangle, I have my baseline and the 3D depth. So I have x over b equals f over d. And so x equals b f over d. So d is the pixel difference between the images. It's just this. So the disparity in this drawing is the length of this horizontal part of the images, which is the difference of where the pixel appears in each image. And so the depth of the point is inverse to the disparity. It's inversely proportional to the disparity. If I know the baseline and I know the focal length, then I can solve for the 3D point exactly. It's just that. So the disparity d is x minus x prime, the difference of the 2D coordinates. But so if I'm representing f in pixels, then x minus x prime would be in pixels. If I'm representing f in meters, then it would be then x minus x prime would be the distance in meters, which would be like the difference in the sensor of like where it hit the sensor. So now what if I have two images that are not side by side? Then the simplest thing to do is to rectify the images so that I create new images as if they were taken from cameras that were side by side, and then do my scanline stereo algorithm. So I first reproject each of the images onto a plane, onto the same plane. And that plane should be parallel to the two camera centers, to the baseline between the camera centers. And then after that, the pixel motion will be horizontal, so corresponding points will be on the same scanline again. And in order to project them onto the plane, I just need to solve for two 3x3 homographies that map each original image onto that plane. And the algorithm to do that is described in this 1999 paper by Loop and Zhang. Zhang is now at Microsoft. So here's an example. I start with two images here. On the top here that look like normal images, but notice that the epipolar lines are not horizontal. Then after projecting each of these images onto the same plane that's parallel to the camera baseline, now the epipolar lines are all horizontal. And so I can I can do my stereo in these rectified images. So now, so my basic stereo algorithm now is, if necessary, rectify the two stereo images to transform the epipolar lines into scan lines. Then for each pixel in the image, search along the scan line and find the best match. Compute the disparity, the difference between the pixels, and then the depth at that pixel is equal to FB over the disparity of the pixels. So to do this, to do matching, I just do a simple scanning window. I would create some window of fixed size, say like 15 by 15, and scan it along the scan line and compute either the sum of squared difference or normalized cross correlation. So I would usually want to do sum of squared difference if I know that my two cameras have the same gain. Because they're taking a picture of the same scene at the same time, and then I expect the intensities to match exactly. But there are times when that won't be true. For example, in the Connect system, it's actually doing stereo using a projected image and a measured image. And the intensities of the projected image will not really match the intensities of the measured image. And so they use normalized cross correlation. The Connect is projecting the image in infrared, so that's why you can't see it. It's projecting a random dot pattern, and that's the basis for its stereo. The Connect is a sensor that's used for robotics and used for Xbox games. So, so this is just visualizing the SSD. So as you move from left to right, the minimum value of the SSD corresponds to the corresponding point, and we can see that there's a correct match. Normalized cross-correlation also works here. So here, if you're doing normalized cross-correlation, then you want to find the position of maximum value. And remember, we talked about SSD and normalized cross-correlation template matching towards the beginning of the semester. So, so one design parameter is how big your window size should be. And it's basically a trade-off that if your window size is really small, then your matches are going to be noisy because there's a good chance that there'll be like lots of patches along the epipolar line that match this tiny window really well. Of course, if you take it to an extreme and you're just doing matching based on 1 pixel, then you can see that it'd be really hard to find the corresponding point. So in this example, when W equals 3, you get nice sharp depth, but you get a lot of noise as well. If you, on the other hand, set the window size to be much larger, then you get smoother depth estimates, but you have a lot of problems on the edges of objects because then you're going to be trying to estimate depth based on pixels that are on the object and pixels that are not. And the disparity of those pixels that are off the object will be different, and so your pixels won't match well. So you're getting these black holes here are places where there is like no good stereo match found. And then also you can see that the trees are kind of like widened beyond what they truly are because the large window is falling off the tree. So, so that's the basic trade-off. If you have a smaller window, you get more detail but less noise. A larger window, you get smoother disparity maps but less detail and fails near the boundary. So there's also a variety of tricks that you can do to try to modify your edge match or modify your template matcher when you're near boundaries to downweight pixels that are off the boundary. So stereo often works, even this simple algorithm can work very well if you're trying to match 2 textured surfaces, but there's a lot of cases where stereo can fail. One of them is if you have textureless surfaces. So if we were trying to match these 2 images, we might do an okay job of getting the depth on Lincoln. But on the wall here, well, in this case, the photos are also kind of weirdly, messed up. But imagine that there's a blank wall here. You're not going to be able to match stereo, right? You can't find where one point on the blank wall matches another, the same point in another image because there's lots of points that look identical. Another problem is repetition and occlusions. These are actually different problems, but there'll be some points in this scene that are not viewed that are in this image that are not in the other image, because if you take a picture from 2 different positions, then near the edges of objects, you'll have occlusion of an object. So, so like this, you can see over here. You can see the base of the Eiffel Tower here, but that's blocked by the gate over here, right? So those occlusions will cause places where you can't do stereo, and they may cause errors. And then you have repetition. So if you're searching along the gate, you might have matched a point here, but there'll be many other points along the gate where you get similar matches. And so you have some kind of ambiguity in what the correct match is that you want to try to resolve. And then a final problem, which is really common, is that stereo doesn't work on non-Lambertian surfaces because of the specularities. So here's 2 pictures of a photograph that's a specular surface, and here's the depth that's recovered. It's really bad. And it's because if you have a specular surface or a surface that has some specular component, then the image that you see will depend on the angle that you're viewing it from, right? Because you'll get some direct reflection of the light. So if you're viewing it from 2 different positions, you'll actually get slightly different images, and that will cause, or different intensity patterns, and that will cause errors in the depth estimation. So this causes problems if you've got water. I mean, water's a disaster, but even like metallic surfaces or shiny surfaces. There's lots of specular surfaces, and they create a lot of problems for stereo. So, so here's a result. So here's an example of this is a stereo image. There's another stereo image. And this is what we get with the window-based matching. So there's a lot of errors on the boundaries of the images, these metallic specular surfaces, there's some errors. There's other parts that are okay, but it's pretty noisy. So compared to the ground truth, red here is close and green is far away. It's a lot noisier and there's more errors. So the next question is, how can we improve on this simple matching? So far, we're just independently matching, finding corresponding points for each pair of pixels. And so what constraints or priors can we add? So one constraint we can add is a uniqueness constraint, that for any point we observe in the left image, there should only be one corresponding point in the right image. So what that means is once I find that this point corresponds to this point, then this point can't correspond to any other point along this scan line. Right, so that gives me a constraint. I can also say that as a prior, that corresponding points should be in the same order in both views. So if I take three points on this image that are in order, A, B, C, then A prime, B prime, and C prime should also be in that order. That will be true as long as you're viewing convex objects, but it can fail if you have a non-convex scene. So here, for example, I've got A, B, and D, but those are seen, where did my C come from? Okay. Oh, it's just blocked from view. So I have A, B, and D, but the points would be observed in a different order in this other image because of this, because of the non-convexity of the scene. So this can be used as a prior, but not as a hard constraint. And then the final prior is smoothness, that usually you'd expect the disparity values to change slowly because on surfaces, the depth will change slowly. But of course, that will be violated on the edges. So we can incorporate all these constraints using, by posing stereo matching as an energy minimization problem. So here we've got, we want to minimize some term that says how well two patches match. So this is the disparity given the corresponding patches. And we also want to minimize a term that says that our disparity is smooth. So here we're only taking into account the smoothness constraint. And so we can write this as a quadratic equation where we want to try to solve for the disparity for every pixel that minimizes the difference of the patches between the pixel and also minimizes the sum over all, it minimizes the difference of neighboring disparities. So if I take the sum over every pixel in the first image, I look at the difference of intensity with the pixel in the second image or patches around those pixels, and I want to minimize that. And then here I'm trying to minimize the difference of disparities for neighboring pixels. So we're going to get into graph-based algorithms for vision later. I don't want to get too much into it now. But you can think about all your pixels as nodes on a graph where they're all just in a grid. And then you have edges connecting to your neighbors. And this is a weight on the edge terms and saying that neighbors should be the same disparity value. And this is a weight on the node saying that how much I want my pixel to have each disparity based on the matching cost. And then you can solve this using an algorithm called graph cuts, which we'll get into more when we talk about segmentation. So this is the result. On the top is the result from independent matching, and on the bottom left is using graph cuts to enforce smoothness. And you can also adapt that to be sensitive to boundaries, so that you say that you only want smoothness. You want smoothness within boundaries, but not necessarily across boundaries in the image. So, all right, so far we've talked about epipolar geometry, and the summary is that, so the epipoles are the intersections of baselines with the image planes. The matching point in the second image is on a line that passes through its epipole, and likewise for the first image. That we encode the relationship between the two cameras with a fundamental matrix or with an essential matrix, which maps from a point in one image to a line in the other image. And we can solve for the fundamental matrix given the corresponding points. And typically, we would find those corresponding points using interest point detectors. And then given F, we can recover the canonical camera matrices. And if we don't know the intrinsics, then that will be with some kind of projective ambiguity. Given two cameras whose pose is known, we can estimate the disparity by finding corresponding points along the scan line, and if necessary, project the images onto the same plane before doing the scanline search. And then we just solve for depth, where depth is inversely proportional to disparity. And if I know the baseline between the two images, then I can solve for the exact depth value. And note that because I know the 2D value of the pixel, once I know the depth, I can also solve for x and y, the other two 3D values. So now I get the full 3D point. Right, so just as a so next class, we're going to talk about structure for motion. So we'll talk about a couple different forms of structure for motion. And so structure for motion is, I guess you could view it as a generalization of the two-view problem. It's when you have multiple cameras that have taken multiple images of the scene taken from different positions, and you want to solve for all of the camera poses and all of the 3D points in the scene. So, and then if you can do that, you can do reconstructions like the one shown here, which are all these little boxes are the poses of different cameras from images downloaded from the internet. And then those images were used to reconstruct the Colosseum in 3D. Whoops, I've got that twice. So I'm going to go through this in the next class. But the basic idea is that you need to compute the features, match the images, and then do the 3D reconstruction, where, of course, there's a lot of details in the 3D reconstruction. So I'll tell you about that next Tuesday. And thanks for your attention, and have a good weekend.